the dark energy inside your brain. What if the force tearing the universe apart is waking up inside your head? A silent pressure stretches galaxies across billions of light years, and yet in an operating room, a few drops of anesthetic can flip your world to black. Here's the bet. If vacuum energy nudges quantum thresholds inside microtubules, anesthesia potency should follow that physics, and we can test it. From exploding stars to hospital hallways and a lab rig we can still build, the stakes are simple. If mind and cosmos link, consciousness leaves a measurable footprint. A 2004 anomaly teased it. A 2016 tangle muddied it. If this lands, it's the one idea you'll argue about all week. To see why this matters, rewind to the night the universe sped up. When the universe started accelerating. It began with dim candles in a dark sky. In 1998, two rival teams, one led by Saul Perlmutter, the other by Brian Schmidt and Adam Rees, used Type Ia supernovae as standard beacons to measure cosmic distances. These white dwarf detonations should shine with near-uniform brightness. Compare their apparent brightness to their redshift, and you get how much the universe has stretched Stingray blue. The teams expected a gentle slowdown. Gravity should be putting its foot on the brake. But the supernovas came in too dim for their redshifts. Dim meant farther than models predicted. Farther meant more expansion than expected. More expansion meant the expansion was speeding up. Phones lit up. Spreadsheets were rechecked. 1,000 small errors were hunted. Dust, evolution, selection bias. The late-night calls ran in circles. When the dust failed to explain the dimness, when the cross-checks held, acceleration slipped into the vocabulary. Reluctantly at first, then with the weight of follow-up surveys, cosmology absorbed the result. If the universe is accelerating, something is pushing with negative pressure. The equations of general relativity allow it. Put a uniform energy density in the vacuum, call it lambda, and it acts like a tension in space itself, driving acceleration. Fold this into the cosmic energy budget, and you get a strange pie. About 5% ordinary matter, roughly a quarter dark matter, and the rest about 70% dark energy. Supernovae started the story, but the cosmic microwave background and baryon acoustic oscillations backed it up. Independent probes converged on a concordance model where lambda sets the tempo of expansion. There were other options. Some theorists tried quintessence, a slowly rolling field that mimics a cosmological constant but can vary in time. Others tinkered with gravity, modifying Einstein's equations on the largest scales. The skirmishes were serious, but the sky kept favoring a simple, stubborn term, a constant vacuum energy density that didn't care about when or where. That simplicity hid an absurdity. Quantum field theory says the vacuum isn't empty. Every field jitters, and those zero-point jitters carry energy. Add up the modes with a naive cutoff, and you overshoot the observed dark energy by a factor that breaks your intuition, orders upon orders beyond anything tolerable. Even with more careful renormalization and cancellations, you still end up with a mismatch that feels like a cosmic joke. Why is the vacuum energy so small yet not zero? Why is it close to the critical density today? The biggest term in the equation seemed to come from nothing, and yet that nothing refused to match theory by numbers that dwarf every other discrepancy in physics. Meanwhile, the human part of the story looked nothing like equations. Researchers who'd stake careers on deceleration sat in offices at 2 a.m., staring at plots that wouldn't budge. A graduate student watched a contour map line up with the parameters she learned to treat as a historical mistake, lambda, then printed it anyway. A principal investigator rehearsed the word acceleration and tried to say it without sounding like a conspiracy theorist. In emails, there was relief and dread. Relief that the data converged across telescopes and pipelines. Dread that the explanation pointed to the least intuitive feature of their toolkit. Accepting acceleration didn't settle the unease. The negative pressure that makes space expand faster isn't a fluid you can bottle. It's a property of the vacuum tied to gravitation and boundary conditions. You can't scatter it in a collider. You can't emit it from a star. You infer it from the way the whole tapestry stretches. And yet, for all its remoteness, dark energy reached into everything. It set the fate of galaxies that would never meet. It throttled the growth of structure, deciding which clumps of matter would have time to pool together before space stretched them apart. It set a horizon for what could ever be observed or influenced. A background parameter became the quiet author of the universe's long-term plot. But the numbers also raised a timing question that everyone tried not to. Anthropomorphize? Why now? Why does the era when matter and dark energy sit in rough parity happen to overlap with the era when telescopes and humans can notice? The safe answer invokes selection effects and the growth of structure. The uneasy feeling lingered. While cosmologists wrestle with emptiness, labs face a different void: experience. Brain activity could be mapped in spikes and waves, but the felt texture of a sensation wouldn't fit a coordinate system. In an operating room, an anesthesiologist could erase the world for a patient without stopping the heart or the reflex arcs. Consciousness went missing with a dosage chart. The void between activity and awareness wasn't cosmic, but it was just as stubborn. The bridge between these two voids wasn't obvious. One lived in redshifts and power spectra. The other lived in reports like, "I felt nothing, and I was there." Still, the idea that vacuum structure might leak into the thresholds that tip brain processes from silent to aware was too provocative to ignore. If acceleration came from a uniform energy of the vacuum, and if parts of the brain depended on quantum thresholds that felt the vacuum, then a parameter by supernovae might, in principle, leave fingerprints in a hospital chart. This is where caution matters. Cosmology doesn't rescue sloppy neuroscience, and brain talk doesn't solve the cosmological constant problem. But if there's a link, it has to pay rent in predictions. Before we get to those bets, we need to face the second void head-on and ask what exactly went missing on the operating table, and why spikes aren't blue. The hard problem walks into a lab. To understand what went missing on the operating table, start with a split that sounds pedantic but isn't. The easy problems ask how the brain integrates information, controls behavior, focuses attention. We can track spikes, synapses, networks. The hard problem asks why any of that feels like anything. No pattern of voltage is inherently blue. No frequency of firing tastes like coffee. Yet somehow subjective experience shows up. That's the hook your brain can't let go of. The gap between doing and feeling is the psychological cliff edge that turns casual viewers into late-night debaters. Clinicians discovered a lever that isolates the gap. Anesthesiologists silence experience while leaving the machine running. Pupillary reflexes can survive. The spinal cord can withdraw from pain. The heart keeps time. Give the right molecules at the right dose, and the patient stops reporting, stops forming memories, stops being there. Then minutes or hours later, with the same body and the same basic wiring, the world floods back. The on-off switch is unnervingly clean. Other cases sharpen the outline. In blind sight, damage to primary visual cortex destroys conscious seeing, but some visual processing still guides behavior. Patients deny seeing a stimulus, yet guess its location better than chance. Split brain surgeries, severing the corpus callosum, can produce two reporting centers in one skull, each half handling tasks and making choices, with a narrator in the left hemisphere confabulating coherence. The hardware works. The felt center flickers, divides, or goes mute. Neuroscience rallies around correlations. Find the neural correlates of consciousness, patterns that show up when someone reports seeing, fades when they don't, and track the richness of experience. We've got candidates, frontoparietal ignition, recurrent loops in sensory cortices, thalamocortical rhythms. But a correlate isn't a cause, and it isn't an explanation. Saying this pattern goes with pain doesn't tell you why pain is like anything rather than like nothing. So theories step in. Global Workspace suggests that when information wins a broadcasting competition, it becomes globally available to multiple systems. Language, memory, motor experience rides along with access. It predicts ignition-like events and explains why attention matters. Integrated information theory posits that consciousness is the amount and structure of causal integration in a system, quantified as phi. It offers a metric and a geometry of experience, but struggles to map onto mechanisms and sometimes assigns experience to systems few would accept. Predictive processing reframes the brain as a prediction machine, minimizing error between models and sensory input. It links perception, action, and attention with a single principle and explains illusions, but it still leaves the field of prediction unexplained. All of these help design experiments and interpret data. None of them explains why a particular neural dance is lit from the inside, and the lab has to measure without wrecking the thing measured. The second you force a report, you recruit prefrontal systems and confound the state you wanted to observe. Ethical constraints limit invasive interventions in humans. Animal models can't report at all. we triangulate with paradigms like no report. tACS, decoding from brain signals during perception without asking for a button press, and clever manipulations that isolate awareness from performance. Here, a different kind of coincidence crept in, a numerical whisper that some physicists took seriously. Certain timescales whispered by consciousness researchers, tens of milliseconds for perceptual integration, sit near timescales one could derive if quantum states underpinning neural events collapse by an objective rule. The math isn't proof, it's a nudge. It says if there's a bridge, you might find it at these intervals. Most neuroscientists shrugged and moved on. A few didn't. Meanwhile, anesthesia kept offering leverage. The Meyer-Overton correlation tied anesthetic potency to oil-gas partition coefficients across wildly different molecules, hinting that hydrophobic pockets in proteins are key. Cell membranes and cytoskeletal structures house these pockets. Clinically, agents as different as halothane, isoflurane, and sevoflurane all flip experience while sparing much of the rest of physiology. The specificity is strange. Consciousness is fragile to these agents in a way reflexes aren't. Psychologically, that clean split body online, you offline, hits the fear center and the curiosity switch at the same time. Ethics force us to be careful. Turn knobs too hard and you harm. Turn them too softly and you learn nothing. So the field-refined non-invasive measures, e.g. microstates, MEG phase relationships, perturbational complexity indices, using transcranial magnetic pulses to measure how richly the cortex responds. Under anesthesia, the brain's echo-simplifies. The response loses diversity. The indices drop. Report vanishes and complexity collapses together. We're getting better at mapping the boundary. Even with better maps, the explanatory gap stays. You can knock out consciousness by disrupting thalamocortical loops, yes. You can restore it as connectivity returns, but are you turning off a broadcast channel or snuffing out a physical process that generates experience? The answer shapes what counts as a basic ingredient. If experience depends on classical network dynamics alone, the hunt stays inside standard biophysics. If, however, there's an objective physical threshold set by something like gravitational self-energy for when superposed possibilities give way to definite events, then the lab is touching a parameter that lives in the same equations as the universe's expansion. That's the risky bridge. It doesn't claim that thoughts control reality. It claims that the event called a conscious moment might be the kind of physical event whose timing is set by deep constants. To cross the bridge, you need a route that goes from numbers to needles, timescales, amplitudes, dose-response curves, and you need predictions sharp enough to fail. Enter a duo who tried to write those predictions down. One brought gravity and objective collapse mathematics. The other brought a place inside neurons where those collapses might matter. Their plan was audacious, heavily criticized, and still testable. It's where the math coincidence becomes a target and the operating room becomes a physics lab. Orchestro, or the most controversial bridge. Start with a rule that sounds like science fiction. Superpositions don't last forever. Roger Penrose argued they don't collapse only when measured. They collapse on their own, objectively, when the difference in their mass distributions makes space-time too strained to hold both at once. Compute the gravitational self-energy of the difference between the two states, invert it, and you get a timescale. That's the objective reduction, the OR in orchestra, R. The claim isn't that the mind collapses wave functions, it's that nature collapses them on a schedule set by gravity's bookkeeping. That gives you a clock, but not a place to hang it in the brain. Enter Stuart Hameroff, an anesthesiologist who'd spent a career staring at consciousness switches. He pointed at microtubules, hollow cylinders built from tubulin proteins that scaffold neurons, guide transport, and shape synapses. Inside neurons, microtubules crisscross like quiet highways. Hameroff suggested they're not just struts. They might host quantum states in hydrophobic pockets, shielded enough to sustain coherent excitations. Orchestrated objective reductions, hence orchestrated, would then occur in structured brain-guided ways producing discrete moments of experience. The picture looks like this. Tubulin states form coherent superpositions across segments of a microtubule lattice. Gravitational self-energy of the mass distribution difference sets a collapse time. Neural context orchestrates when and where ensembles reach the threshold. Each collapse is a moment, elementary now, that integrates into streams we call consciousness. The brain still computes classically, but punctuated by these objective quantized events. Critics didn't wait. Max Tegmark ran the numbers in 2000 in a warm, wet brain. Decoherence times for superpositions of charges or dipoles plummet to femto to picoseconds, far too fast to align with tens of milliseconds dynamics. Thermal noise, ions, collisions, everything screamed no quantum. Others argued that even if microtubules could host coherent modes, scaling coordination across a neuron or network would drown in biological mess. Penrose-Hameroff replied on two fronts. First, they said Tegmark's target was off, not free charges inside us all, but conformational states in hydrophobic pockets and collective excitations along microtubule lattices, potentially protected by ordered water layers and lattice symmetry. Second, quantum biology was quietly rewriting what too warm meant. Photosynthetic complexes showed long-lived coherence at room temperature guiding energy transfer. Avian navigation pointed to spin-dependent reactions sensitive to weak fields. Enzymes exploited tunneling. If nature could engineer local coherence in messy environments, maybe neurons had found a niche. Evidence trickled in, suggestive but not decisive. Experiments reported anesthetic molecules binding at specific hydrophobic sites on tubulin and nearby proteins consistent with the Meyer-Overton correlation. Optical studies in vitro hinted at microtubule resonances, photonic, phononic, or both, in frequency bands that overlap with neural rhythms. Some groups saw anesthetics damp or dine these signals, other groups saw nothing beyond artifacts. The field split along familiar lines. One camp saw noise, the other saw a signal loss in noise that better rigs could surface. Even if coherence exists, the gravitational piece is a wild card. Penrose's formula ties collapse time to a physical quantity, the mass distribution difference, making it, in principle, parameterizable. That's where our story's cosmology sneaks back in. If objective reductions are real, and if the vacuum carries a uniform energy density, lambda, does that background affect the threshold or the elasticity of space-time that the superposition strains? Penrose himself focuses on self-energy, not cosmology, but the conceptual door is open. Collapsed timing might indirectly carry a fingerprint of the vacuum's properties. Caution, again, there's no accepted derivation tying lambda directly to neuronal events. But the structure is tempting. Orchestra offers a time constant that could line up with perceptual integration windows. Microtubules offer a substrate with drug-accessible pockets. Anesthesia offers a lever to modulate the substrate. If a cosmological parameter nudges the collapse threshold, potency curves and resonance Q factors might show subtle testable regularities. The stakes aren't small. If gravity helps decide when neural possibilities gel into facts, then cognition is brushing up against the same machinery that shapes galaxies. Consciousness wouldn't be outside physics. It would be a series of objective physical events timed by constants that also live in cosmology. That doesn't make thoughts cosmic engines. It makes conscious moments part of nature's schedule. Human beats kept the debate grounded. A postdoc in Tucson watched a microtubule prep drift under the microscope and swore at a vibration coming through the bench. Across the world, a theoretical physicist scribbled collapse integrals on a whiteboard, paused, and muttered that biology would never keep phase. Emails flew, preprints stacked up, and conference Q&As turned into careful fencing matches between chemists who knew proteins and physicists who knew decoherence. Then came updates that neither side could fully ignore. Better anesthetic binding maps pinpointed hydrophobic sites with potencies tracking clinical effects. Resonance measurements improved, though they still fought artifacts. The line between nothing there and not there yet stayed blurry, which is why pre-registered, blinded tests became the drumbeat. If orchestra is right, dose-response curves should align with resonance damping in ways classical models don't predict. If it's wrong, the curves won't care about those putative modes, and hovering over all of it is that backstage parameter, the cosmological constant. If the vacuum's quiet push shows up anywhere near a thought, it'll show up in the timing of objective reductions. That's a claim you can miss or hit. To follow it, we need to put lambda on the math and see if the bridge holds when numbers push back. The coincidence that bothers cosmologists and philosophers. There's a pie chart that ruins sleep. On one slice sits matter, the stuff that clumps, forms stars, and gives you weight. On another sits dark energy, the uniform push that stretches space. Today, those two slices are strangely comparable. Not equal, but close enough that their tug-of-war shapes everything we can see. Roll the clock backward or forward, and that balance vanishes. So why do we live in a thin sliver of time when both matter and dark energy matter? Cosmologists call it the why now problem. It isn't a technical glitch. The equations allow many errors: an early, matter-dominated universe where gravity built structure fast, and a late de Sitter, like era where dark energy wins and galaxies drift out of view. In between lies a brief crossover, when matter still seeds galaxies while dark energy starts a long fade-out. We arrived in the middle. That feels like walking into a theater precisely as the plot twist lands. One answer refuses mysticism and leans on selection. Observers exist only where structures form. If dark energy dominated too early, clumps wouldn't grow. No stars, no planets, no chemistry, no questions. If it arrived too late, the universe would be crowded and violent, but observers wouldn't care about now because they'd be distributed across long epochs. Anthropic logic says, of course we find ourselves when both growth and acceleration coexist. That's when life can appear and last long enough to notice anything. This line makes many physicists queasy. It can sound like a story you tell when you've run out of calculations. Still, it has teeth. Models with different dark energy densities predict different structure histories. Only a narrow range produces galaxies like ours in time for carbon chemistry. In that sense, why now becomes because otherwise we wouldn't be asking. Layer in the consciousness angle and the selection gets sharper. If the timing of conscious episodes depends, even weakly, on an objective physical timescale that includes gravitational self-energy, then there's an implicit requirement. Biological processing times must harmonize with collapse times. Too slow, and integration fails. Observers might cluster in epochs where cosmic parameters place these clocks in the same neighborhood. That doesn't assign purpose to the universe. It says some universes host more askers because their parameters let asking be felt. Across town, a single person sits at a desk with a pie chart on a screen. It's 2 a.m. The office is quiet except for the fan. They drag a slider in a simulation. The matter density goes up. Structure booms, dark energy gets pushed back. Drag it down, structures starve. Nudge dark energy up, galaxies stall. Nudge it down, acceleration arrives late. The curve that threads observers through time isn't broad. It's a ridge. They stare, not because it proves anything, but because the ridge lines up with the only moment they've got. There are hazards here. Selection effects can morph into just-so tales. The multiverse framing, many universes with different parameters, most sterile, a few fertile, can't be tested directly. And a curiosity that starts in good faith can drift into purpose narratives dressed as physics. The guardrail is simple: don't overclaim. Use selection reasoning to flag where data should cluster. Don't smuggle meaning into the clustering. Meanwhile, anesthesiologists were flipping consciousness like a switch. In brightly lit operating rooms, doses were tuned down to decimals. Monitors beat, muscles relaxed, pupils still constricted to light. The patient's report went to 0. When they woke, the gap was clean. No time passed from their point of view. That clinical on-off made why now feel less cosmic and more immediate. Why does experience happen now for this person, and not 10 seconds later when a few molecules more would erase it? If microtubule modes really couple to objective reductions, and if collapsed timing whispers a faint lambda dependency, then those operating rooms are brushing the same ridge the cosmologists watched. The chemistry is local. The timing might not be. That's the provocation. The coincidence of errors and the coincidence of thresholds might be two views of the same constraint. Curiosity versus caution keeps score. On the curiosity side, coincidences have steered physics from Mercury's orbit to general relativity, black-body curves to quantum theory. On the caution side, most coincidences evaporate when better data arrives. So we treat why now as a signpost, not a conclusion. It points to tests, not to stories. Here's the stake. If the now that makes galaxies hospitable also lines up with the now that makes experience stitch, then mind leaves a tiny lawful footprint on cosmic parameters, not by changing them, but by depending on them. If not, we lose nothing by asking. Either way, the next steps live in labs, not in late-night pie charts. Meanwhile, anesthesiologists kept clicking syringes, unaware they were pacing the universe's strangest question with a metronome of their own. Anesthesia, microtubules, and the off switch. In the operating room, the strangeness hides in plain sight. You're breathing. Your heart keeps time. Light hits your eyes and your pupils obey. Yet when the anesthesiologist nudges a plunger, the world falls away as if someone yanked the power to whatever you call me. Reflex arcs survive. Experience doesn't. That divide is the cleanest handle we have on consciousness, and anesthetics give us a dosage knob with millimeter markings. This is the moment people replay for friends, the jump cut in memory that feels like teleportation, and it's the psychological anchor for the whole story. Clinically, the rule of thumb began as a chemistry riddle. Take dozens of unrelated molecules, aldehydes, ethers, noble gases, and rank how potent they are at erasing the report. Their potencies line up with how easily they dissolve in oil. That's the Meyer-Overton correlation. It doesn't care about receptors or shapes, it cares about slipping into hydrophobic pockets. Those pockets live in membranes and proteins, including the workhorse tubulin that snaps together to form microtubules. Microtubules are the quiet scaffolding of neurons. They're hollow cylinders, 13 protofilaments around a nanoscopic lumen, running from cell body to synapse like rails. They move cargo, stabilize shape, and help build connections. For decades, they were background infrastructure. Then, anesthetic binding studies started flagging tubulin's non-polar cavities as plausible docking sites with affinities that shadow clinical potency. The implication was modest but sharp. Some part of the off switch happens in places where oil-loving molecules can settle and slightly tune protein dynamics. Labs began aiming instruments at these cylinders. Shine light. Listen for faint phonon-like vibrations. Probe with terahertz fields. Watch how signal quality, its Q factor, changes when you add anesthetic. A few groups reported narrow resonances, hints of coherent excitations that lived longer than noise should allow. Add isoflurane, and the peaks damped. Swap for xenon, and the damping track dose. Other groups, using different preparations or controls, saw only baseline mush. Everyone agreed on one thing. The experiments were hard. Thermal jiggle, electromagnetic interference, and the fragility of polymerized microtubules conspired against clean measurements. While the rigs argued, lived experience kept offering a stark metric. The anesthesiologist leans in. Take a deep breath. Count backward from 10. You say 10, 9, maybe 8. Then there's a jump cut. A voice says your name. You answer with the same mouth, the same nerves, and a continuous memory that has a hole where 20 minutes should be. No pain, no dreams, no time. Families notice it too, the way a person goes present to absent without drama, then returns with the world stitched as if nothing happened in between. That shared, "Where'd I go?" moment is the viral clip everyone recognizes, and it keeps viewers leaning forward. The bridge hypothesis puts microtubules near the mechanism. If their hydrophobic pockets host modes that can couple, however weakly, to objective reductions, anesthetics might quench those modes. Not because they turn off mind stuff, but because they detune the conditions under which widespread orchestrated reductions line up with neural computations. Turn the damping past a threshold, and streams that would have been integrated become noise that never crosses the line into reportable experience. Meyer-Overton gives the first axis. Oil solubility predicts potency. Orchestra adds a second axis. Agents that preferentially occupy pockets linked to specific microtubule modes should damp those modes in ways that co-vary with clinical minimum alveolar concentration. If those modes map through mass distribution differences in Penrose's timescale onto tens of milliseconds dynamics, then the dose that flattens the resonance should match the dose that collapses the brain's perturbational complexity. Skeptics push back with well-aimed points. Anesthetics hit many targets, GABA receptors, 2-pore potassium channels, NMDA receptors. Why elevate tubulin? Gamma oscillations and integration can be explained by network-level inhibition and thalamocortical loops. Add to that the warm, wet objection. Even if microtubules resonate, coherence in vivo should be shredded by thermal noise and ionic chatter. The off switch doesn't need quantum garnish to work. That skepticism is healthy, but the levers anesthesiologists use still invite specific tests. Consider xenon, an inert gas with anesthetic properties. It's hydrophobic, bonds in nonpolar cavities, and its potency shifts under pressure, something you can modulate safely. If microtubule Q factors in vitro track xenon concentration and pressure in ways that align with changes in human responsiveness, you move beyond garnish. Look at ketamine, which breaks Meyer-Overton's neat line and dissociates consciousness differently. If ketamine leaves tubulin-linked modes relatively intact while still disrupting network integration, that contrast narrows where the off switch really sits. Behind the bench, the human beats keep the work honest. An anesthesiologist knows the weight of a decimal point on a syringe. A researcher knows the sickening moment a beautiful peak turns out to be a ground loop. A patient knows only the gap, the soft banter, the mask scent, the counting, the cut to later. Those three vantage points meet in the same question: what exactly gets turned off? If microtubules host modes that anesthetics reliably tune, then the molecule-to-mind bridge tightens. If further, the timing of the modes that matter lines up with objective reduction timescales tied to mass differences, then the off switch touches physics deeper than pharmacology. None of that says thoughts steer galaxies. It says the most intimate loss a human can undergo, absence of experience, may hinge on nanoscale structures whose behavior can be tuned and predicted. There's one more wrinkle tucked in the margins of old lab notebooks. In 2004, an odd blip showed up when researchers tried to measure tiny forces in engineered cavities, an anomaly that flirted with vacuum effects. Most wrote it off as noise. A few didn't. 3 years before that, the Casimir effect had been nailed to the table with precision that turned philosophy into metrology. Those two threads will cross our path next. Casimir, vacuum, and a tiny pressure with big implications. Two polished metal plates placed micrometers apart in a vacuum start to creep toward each other as if pulled by an invisible hand. No wires, no charges, just emptiness pressed into doing something. That's the Casimir effect. The explanation lives in the jitter of quantum fields. Between the plates, only certain wavelengths fit. Outside, all modes froth. The imbalance in allowed fluctuations produces a tiny net pressure, and the plates feel a force. It's small, but not imaginary. In 1997, Lamouro's torsion pendulum measured it cleanly. Later experiments refined the geometry, accounted for real metal roughness and patch potentials, and pinned theory to numbers with precision. This is the lab's way of saying the vacuum isn't blank. Boundary conditions change what nothing can do. And if boundaries can sculpt vacuum fluctuations between metal plates, the question practically asks itself, could biological structures, narrow, ordered, hydrophobic, and packed, impose boundary-like conditions on local fields in ways that matter for delicate physical processes? Precision groups use spheres near plates, switch to microfabricated cones, and chase every mundane culprit. Temperature drifts, surface contamination, electrostatic patches, even humidity got audited. Each improvement left the core signal standing. Geometry dictates a measurable vacuum pressure. Naive quantum field theory estimates that ignore material response and finite temperature fail. Corrected calculations with Lifshitz theory, dielectric functions, and real conductivities match data. The lesson is humbling. The vacuum is a partner, but a picky one. You must count every constraint. Now slide that lesson next to microtubules. They're not metal mirrors, but they're periodic cylinders with nanoscopic inner cavities, lined by nonpolar surfaces and organized into bundles near membranes and organelles. If objective reductions involve mass distribution differences in quantum states coupled to fields, then local fluctuation spectra could, in principle, tweak the effective environment those states feel. Not a huge shove, more like a nudge to the Q factor of modes living in hydrophobic pockets and lumen-adjacent regions. There's a crossover hypothesis. If vacuum texture shapes collapse, relevant coherence, then Casimir-like conditions might modulate those textures at the nanoscale. Here's a concrete device proposal. Build a chip with two regions. In region A, create nanocavities, parallel trench arrays, or coaxial nanochannels, engineered to produce Casimir pressures with calculable spectra at biologically relevant separations in materials. In region B, leave an open microfluidic volume that lacks tight boundaries. Flow purified tubulin and polymerized microtubules in both regions under identical temperature, pH, and ionic conditions. Then probe for resonances with low-noise optical terahertz methods while sweeping a panel of anesthetics, isoflurane, sevoflurane, xenon, and a non-anesthetic control of similar lipophilicity. The readouts to watch: resonance frequencies, line widths, and Q factors, phase noise, damping constants as a function of concentration. If Casimir-shaped cavities shift vacuum fluctuation spectra in ways relevant to collapse-prone modes, region A should show systematically different baselines, slightly higher or lower Q, altered line width slopes, and region B. If the lambda orchestral, our coupling idea has teeth, anesthetic-induced. Damping curves might converge on a common latent timescale, even when chemistries differ, and the cavity versus open contrast would remain after controlling for viscosity and dielectric changes. Skeptics will point at decoherence like a referee throwing a flag. In vivo, everything shakes, ions crash, water sloshes, proteins flex. Any fragile quantum superposition dies fast. Fair! That's why the device starts in vitro, where you can clamp temperature to 1/10 of a degree, isolate vibrations, Faraday, cage the platform, and use heavy water or deuteration where appropriate to tune phonon spectra without changing chemistry. You're not claiming cells are Casimir laboratories. You're asking if the relevant physics exists in principle and if anesthetics touch it in predicted ways. Meanwhile, precision Casimir groups have one more lesson to learn: control the nuisances or your signal lies. Patch potentials masquerade as vacuum forces. In our case, electromagnetic interference and photothermal artifacts can fake resonances. So the rig needs phase lock detection, blind anesthetic swaps, and sham injections. It needs calibration with proteins that lack hydrophobic pockets and with Taxol stabilized versus dynamic microtubules to see if lattice state matters. It needs temperature and pressure sweeps that map classical damping alone. Only after subtracting those baselines do you ask whether residual aligns with an objective reduction timescale inferred from mass distribution toy models of tubular conformations. What would success look like? Not a giant spike labeled lambda. It would look like a family of curves. Damping versus concentration for multiple agents crossing at a characteristic frequency band edge. Cavity versus open showing a small but repeatable shift in Q. Xenon pressure dependence tracking both clinical potency shifts and no result for a non-anesthetic analog. Stack those observations and run pre-registered analyses that test a specific mapping from collapse time predictions to frequency windows. If the stack holds, the bridge gets a plank. If it collapses, retire the claim. There's also a human reason to push here. The Casimir story began as a thought experiment about plates in a vacuum and became a metrology playground. It took decades to isolate a pressure nobody believed was practical to measure. The people who nailed it weren't mystics, they were engineers and patient theorists. The same grid applies now. Build a device. Let others build competing versions. Publish raw traces. Invite people who think it's nonsense to wire your grounds. While plates squeezed vacuum into doing work, psychologists kept timing perception, probing how fast experience stitches. If boundary-shaped nothingness can tug metal and nudge resonances, maybe the frame rate of awareness, those tens of milliseconds we keep circling, has a neighbor across the hall. And that's where we're headed, into the lab where time itself gets measured by what your mind can bind. The frame rate of experience. Open your eyes to a strobe and something odd happens. Below a certain rate, you see individual flashes, discrete moments. Push the rate higher and the flashes fuse into steady light. Psychophysics gives that boundary a number, the flicker fusion threshold, roughly 50 to 60 Hz for luminance in good conditions, lower for complex patterns and color. Another measure, the temporal binding window, sits around 30 to 50 milliseconds. Sounds and sights within that window feel like one event. Outside it, they split. Those aren't opinions. They're repeatable timings your nervous system enforces. This is a viewer's hook. You can test it on yourself in seconds, then send it to friends to argue who has faster frames. In the brain's electrical chorus, you see echoes of those windows. EEG and MEG pick up rhythmic bursts, alpha around 10 Hz, beta in the teens, gamma from roughly 30 to over 80 Hz. These aren't continuous metronomes. They arrive in packets, brief bouts of phase-locked activity that line up with moments of perception. Stimulus hits. A cross-frequency handshake occurs. A gamma burst rides on a particular phase of alpha or theta, and decoding accuracy spikes. Missed a phase and the information doesn't make it to report. Map that to behavior and you get crisp moments. Present two flashes a few milliseconds apart and people see one. Stretch the gap past the binding window and they see two. Deliver two taps to a fingertip in a similar window rules whether they merge or separate. In multi-sensory tasks, a sound can pull a light into its own moment if the asynchrony sits inside about 100 milliseconds. Outside that, it can't. The mind's stitching rate isn't arbitrary. It's tethered to timings you can probe with a keyboard and a screen. Orchestral, or steps into this terrain with a risky mapping. If objective reductions occur on timescales set by mass distribution differences in putative microtubule states, then the inverse of those. Time sits in the gamma neighborhood for biologically plausible parameters. That suggests a link. Discrete reduction seed packets of coordinated neural activity that land as perceptual snapshots. When gamma couples to alpha, you get frames nested in larger frames, moments within moments that match how attention gates what you notice. Human stories keep the numbers from floating away. Watch a concert pianist in flow. Subjectively, time thickens. Motor sequences roll out with less conscious micromanagement, and yet small anomalies, an unexpected cough, a missed key, pierce the stream. Recordings show increased phase locking across motor and auditory cortices. Gamma power comes in tight bursts aligned to motor chunks. Beta dips before movement onsets. Ask the pianist and they'll say they weren't counting. Their frames were full. Not everyone buys the frames language. Continuous perception models argue that awareness is smoothly updated, and what looks discrete is just the mechanics of decision and report. They point to microstate analyses and EEG, quasi-stable topographies lasting 60 to 120 milliseconds that flip like cards, and say these are network modes, not moments. They're right about the network modes. They might be wrong that discreteness is only downstream. The bead hinges on whether the subjective boundary tracks a physical event or an emergent threshold. Evidence cuts both ways. Some experiments show graded detection probabilities that smear across time. Others show rhythmic sampling where perception waxes and wanes with alpha phase. Saccades impose their own gates, suppressing and then releasing visual processing with a rhythm that can seed illusions of continuity. Meanwhile, perturbational paradigms zaps the cortex with magnetic pulses, produce echoes whose complexity correlates with consciousness level. Under anesthesia, the echo simplifies. The frame rate, if it exists, seems to slow, widen, and then fall apart. If collapse dynamics lurk underneath, here's what should follow. First, the periods tied to objective reduction should show up as preferred windows in which stimuli are more likely to be integrated and reported. Second, manipulations that shift microtubule resonances, temperature nudges within safe bounds, mild hyperoxia or hypoxia, low-amplitude transcranial alternating current stimulation at gamma frequencies should bend those windows in predicted directions. Third, anesthetic agents with different molecular targets but similar hydrophobicity should converge on the same behavioral timings when you normalize dose to the dampen they induce on the relevant modes. Consider a microstory you've likely lived. You're cycling through red, green, blue squares that swap faster and faster. At low speed, you name them. At mid-speed, you feel a tug. Sometimes red-green merge into a weird lemon that isn't on the screen. At high speed, it's just a blur. Push a tone a few milliseconds ahead of a dim flash, and the flash becomes easier to see. Slide the tone behind, and it helps less. Those tiny assists are your brain playing Tetris with time, dropping pieces into slots that open and close in tens of milliseconds. It's the kind of challenge that goes viral. Post your fusion threshold, tag a friend, and watch the comment wars. Now, look at cross-frequency coupling. Gamma bursts tend to land on particular alpha phases, and perception is best at those phases. That coupling sets a course, defined hierarchy. Alpha parcels attention. Gamma fills the parcels with detail. If orchestra OR is relevant, objective reductions align with the gamma packets, while the orchestration, the O in orchestra, rides alpha and theta, recruiting and routing. That's a story you can break. Disrupt the routing without touching putative collapse dynamics, and you should hurt integration, but not the basal timing. Damp the collapse-prone modes, and you should flatten both. Counter evidence doesn't vanish. You can mimic many timing effects with recurrent networks, inhibition and delays. No quantum thresholds required. And gamma might be a readout of computation rather than a cause. But the testable wedge remains in the triangulation, behavior, rhythms, and nanoscale signatures moving together with perturbations and pharmacology in a way classical models can't fit without special pleading. The stakes are practical. If subjective frames shadow collapse dynamics, then behavior becomes a physics window. You can't tweak lambda, but you can tug on temperature, oxygen, and general stimulation to see whether the windows bend in ways the bridge predicts. The next step is to stress the system safely with those levers and watch the stitching change or refuse to, messing with consciousness safely. If behavior can be a physics window, we need levers that bend timing without breaking brains. Start with tools that touch rhythms from the outside. Transcranial magnetic stimulation sends a quick magnetic pulse that induces a tiny current in cortex. One zap and you can. Watch the brain's echo travel, rich when awake, simple under anesthesia. Push TMS in rhythmic trains, and you can bias local networks towards certain frequencies for a few hundred milliseconds. Transcranial alternating current stimulation drapes a weak sine wave across the scalp. Neurons that are close to firing can phase slip into alignment with it. Focus ultrasound reaches deeper, nudging excitability with millimeter precision while staying below thresholds that heat tissue. Those aren't hammers, they're nudges. The plan isn't to induce gamma by brute force and declare victory. It's to shift the phase relations that parse through time, alpha handing out slots, gamma filling them, and see whether the temporal binding windows bend in ways that match prediction from microtubule-linked modes. If the collapse-prone substrate has a preferred cadence tied to mass distribution differences, then the most efficient entrainment should occur at slightly offset frequencies that reflect those intrinsic timescales, not at whatever we dial on the stimulator. In practical terms, a 40 Hz tACS might work best when the underlying system wants 38 or 42 based on temperature and oxygen, numbers we can control. Environmental tweaks give us slower, safer knobs. Mild hypoxia, oxygen fraction gently reduced within ethical limits, can lengthen neural recovery times and change metabolic noise without causing harm. Hyperbaric oxygen tightens the opposite direction. Both shift viscosity, redox states, and phonon spectra that proteins swim in. Temperature, nudge half a degree up or down in tightly monitored settings, changes rate constants and damping in predictable ways. These aren't stunts, they're routine in physiology labs and clinical units. Each knob should move classical network timing, yes, but if microtubular resonances contribute, their Q factors will move along a distinct curve. Marry those curves to behavior and you get triangulation. Here's a forecast if the bridge matters. Gentle tACS at near gamma frequencies should improve detection for stimuli, time to land near specific alpha phases, but the sweet spot frequency should drift with temperature in the same direction as in vitro microtubule resonances. Focus ultrasound to thalamus, delivered at submotor intensities, should widen or narrow the temporal binding window depending on whether it perturbs routing or the substrate. Mild hypoxia should lower flicker fusion thresholds, slightly and broaden binding windows. If we measured microtubule Q factor shifts under the same oxygen tensions, the behavioral change should map onto the damping curve predicted by the resonance model, not just generic slowing. Safety sits in front of curiosity. Every protocol passes oversight. Hypoxia is reversible and mild. Hyperoxia is within respiratory therapy standards. Temperature stays in fever range boundaries only under physician supervision. Stimulation follows conservative guidelines, current densities under established limits for tACS, duty cycles for ultrasound that avoid heating, TMS intensities well below seizure thresholds, with real-time EEG watching for adverse signatures. Animals get humane endpoints and analgesia. Humans get informed consent and stop buttons. The point is to move timing by millimeters, not miles. The comparison class matters. If lambda sets a background tolerance for objective reductions and we can't change lambda, then changing these local knobs should not abolish timing if lambda dominates. You'd see course shifts from classical factors, but the latent collapse timescale would stay put, anchoring the best fit frequency across conditions. If microtubule modes inside neurons contribute meaningfully, each knob that affects their damping should move the anchor. Not wildly, by fractions of a millisecond, but enough that psychophysics can register it and EEG-MEG can show consistent phase shifts. This is where blind protocols earn their keep. Subjects don't know whether they're getting sham stimulation. Experimenters who run psychophysics don't see EEG in real time. Analysts pre-register which epochs, frequencies, and windows will count before any data arrives. Perturbational complexity gets computed by code posted ahead of time. Across conditions, we test a small set of pre-specified predictions. Temperature up shifts the optimal entrainment frequency down by X%. Hypoxia widens the binding window by Y milliseconds. Anesthetic microdose lowers perturbational complexity and shifts the alpha-gamma coupling phase by Z degrees. All numbers trace back to in vitro damping measured on microtubules at matched conditions. Expect pushback. Network models without quantum pieces can produce similar shifts under hypoxia and temperature. That's why we lean on convergences. If three unrelated levers move behavior and rhythms along one curve, defined by resonance changes in tubulin assays, while a fourth lever that shouldn't affect those modes, say a cholinergic agonist, N, microdose moves behavior but breaks the curve. then the bridge loses ground. If instead, the curve holds across levers that touch hydrophobic pocket dynamics and brakes for those that don't, the story tightens. There's a human rhythm under all this instrumentation. A participant sits in a quiet room, a faint tingle on the scalp, a tone pip here, a flash there. They tap a button when they see 2 flashes or 1. A clinician watches oxygen saturation hold steady at safe levels. A researcher squints at a screen where oscillations drift and lock. No one in the room feels a cosmological constant. But if the stitching of experience bends predictably with these gentle pushes, and the bends echo what we measure in proteins, then the vacuum's background might be whispering through timing. We close this pass with a tease. In 2016, 3 labs tried to skirt the edge of these predictions with different rigs and landed in a tangle, some damping that tracked anesthetics, some nothing at all. The result wasn't proof. It was a challenge. Pre-register, blind, stream the traces, and make the pass-fail hurt. The 2016 mystery and what it didn't prove. 3 labs' one ambition, catch microtubules doing something that anesthetics could reliably silence. The protocols look similar on paper. Purified tubulin, polymerized into microtubules, probed with low-noise optics or terahertz spectroscopy, with anesthetic concentrations stepped through clinically relevant ranges. The hope was simple. If narrow resonances tied to hydrophobic pockets exist, their Q factor should drop as anesthetic occupancy rises. A clean dose-response curve would hand the field a foothold. What happened instead was a lesson in how fragile signals die. Lab A reported a slender ridge in the spectrum, repeatable peaks in the tens to hundreds of gigahertz that narrowed with careful polymerization. Add isoflurane, and the peaks broadened in proportion to dose. Swap in xenon, and the effect trapped partial pressure. The authors ran controls with non-anesthetic analogs and saw less damping. Their takeaway: anesthetics to tune microtubule link modes. Lab B aimed for replication with tighter environmental control. They Faraday caged the bench, floated the optics on air tables, and tightened temperature to 1/10 of a degree. Their spectra looked cleaner, but the ridges were gone. Everything that looked like a peak collapsed in the baseline when they redid the calibration with different lamp and corrected for a subtle photothermal artifact. Anesthetics added nothing but a flat offset. Their takeaway: the prior signal was instrumentation. Using electrical impedance in microfluidic channels, they saw faint features that shifted with Taxol stabilization and ionic strength. Anesthetics seemed to nudge those features, but the effect size hugged the noise floor. They published cautiously, framing the result as weakly suggestive, with 3 pages on confounds and a call for blinding. Underneath the figures was a quieter story. A grad student in Lab A watched peaks sharpen at 2 a.m., knowing a reviewer would ask whether the mains hum was sneaking into the detector. They added a battery-powered light source, reran, and the peaks lived. In Lab B, a postdoc found that a cable's braid wasn't grounded, resoldered it, and watched a resonance vanish. In Lab C, the team learned how much a hand near the stage could shift air temperature enough to fake a line would change. Everyone drank too much coffee. Everyone swore at their own wishful thinking. Temperature turned into the villain and the alibi. At terahertz frequencies, photothermal effects can broaden lines through mundane heating. An anesthetic vial drawn from a fridge and not fully equilibrated can create convection that masquerades as signal. One group pipetted anesthetic under a blind code, only to learn later that the coded vials differed slightly in ethanol content used as a carrier. Ethanol alone can alter polymer stability and change scattering. What looked like physics became chemistry. What looked like chemistry became plumbing. Electromagnetic interference made a cameo, too. Patchy ground loops produced cone-like artifacts. Lab A claimed they killed those by isolating detectors and using optical fibers. Lab B showed that an unnoticed LED driver in a nearby incubator sprayed enough noise to write fake ridges into the baseline. The argument migrated from journals to conference hallways, where the question wasn't, do you believe Orchestro, but show me your noise budget. Amid the tangle, one result kept tugging. When labs blinded anesthetic identity and dose, the few curves that held up shared a pattern. Damping moved with oil-gas partition coefficients, and for xenon, with pressure. That matches Meyer-Overton and says nothing about microtubules by itself. But in 2 blinded runs, the damping pivoted around a similar frequency band when tubulin was polymerized compared to when it wasn't. Not a smoking gun, more like a smudged fingerprint you can't dismiss or use in court. Critics reasonably ask the hard questions. Why not look directly at known anesthetic targets like GABA A receptors and map damping there? Why insist on microtubules when networks explain anesthesia so well? The reply from bridge builders was pragmatic because microtubules give you hydrophobic cavities that anesthetics occupy, a polymer lattice that can, in theory, support collective modes, and a substrate you can move between engineered vacuum boundary conditions and open solution. If the signal exists anywhere you can ping with physics, it might exist here. What 2016 proved was what it didn't. It didn't prove microtubule coherence in vivo. It didn't prove that anesthetics damp collapse relevant modes. It didn't prove any lambda dependency. It did prove that signal-to-noise in these assays can fool capable teams, that temperature and EM hygiene decide outcomes, and that unblinded enthusiasm paints spectral ghosts. It proved the field needed pre-registration, blinding, sham controls, and public raw. Traces. It proved the question survived the first swing, which is different from surviving a clean hit. In the aftermath, a handful of labs pre-committed to standards, identical carriers for all drugs, pressure and temperature logged to the second, ground maps of every instrument, independent teams handling blinding and injections, open repositories with raw interferograms and code. The stakes tighten. Either a dose-damping curve lands where it's predicted to land across agents and rigs, or it doesn't. No gray zone, no interpretive dance. For a grad student who'd bet 2 years on a peak, that felt brutal. For a field flirting with a bridge from mind to vacuum, it was the only way forward. The next chapter lays out that pass-fail trial. Public, brutal, definitive, so we don't chase ghosts again. The experiment we can still run. We start by writing the bet down in public before a single cable is plugged in. The pre-registered plan says exactly what we'll measure, how we'll decide pass or fail, and which results count. No exploratory fishing dressed up as prophecy. The assay is in vitro, purified tubulin polymerized into microtubules under tightly controlled conditions. We'll probe their resonances, optical, terahertz, or nanomechanical signatures, while we vary anesthetic concentration, pressure, temperature, and boundary geometry. Every parameter is logged. Every swap is blinded. Every raw trace is posted. The core readouts are simple on paper. Resonance frequency peaks, line widths, Q factors, and phase noise. The prediction matrix pits 2 stories. In the classical view, anesthetics perturb membranes and azure protein targets. Any damping we see should scale with non-specific changes, viscosity, dielectric properties, and generic hydrophobic occupancy without converging on a latent timescale tied to a gravitational quantity. In the orchestral plus vacuum view, damping of a specific subset of microtubule modes will co-vary with anesthetic potency across very different chemistries, and the family of dose-response curves will intersect at a characteristic frequency band that maps via mass distribution estimates. Blinding is non-negotiable. A separate team prepares coded anesthetic solutions with identical carriers, matched ethanol content, and verified equilibrations. Xenon injections are administered through a pressure-controlled microfluidic manifold with pressure hidden behind a calibration code. The operators who align optics or read interferograms don't know which vial is which. A second lab receives aliquots from the same batches and runs the same protocol on a different rig. We pre-register not only hypotheses but also exclusion criteria. Any run with temperature drift beyond 0.1 degrees C per minute is discarded. Any spectrum showing calibration lamp harmonics is flagged and removed. Casimir-style boundary conditions enter as an add-on, not a rescue. The chip carries 2 environments, nanocavity regions engineered with known separations and dielectric stacks, and open channels with the same fluidics but no close boundaries. We compute expected vacuum mode contrast using Lifshitz theory with measured material properties. Then we ask one clean question. Do baseline Q factors and their anesthetic-induced changes differ between cavity and open in a repeatable way that survives controls for viscosity and ionic strength? If yes, we have evidence that boundary-shaped environments nudge the relevant modes. If no, the lambda-flavored piece loses a leg. Pharmacology provides a lever arm. The series includes isoflurane, sevoflurane, desflurane, halothane, xenon, and a non-anesthetic analog matched for lipophilicity. For each, We sweep concentrations spanning subclinical to near-clinical ranges. For xenon, we add pressure steps within safe lab bounds. The pre-registered prediction, when we normalize each curve by measured binding to tubulin hydrophobic pockets, the damping versus occupancy slopes collapse onto a single master curve, and the curves pivot around a shared frequency band. The non-anesthetic analog should fail to join the collapse, even if it occupies similar pockets. Controls multiply because they have to. tACS stabilize microtubules versus dynamic lattices. Tubulin mutants or heterologous proteins lacking hydrophobic cavities. Buffer only shams. Heavy water substitution to shift phonon spectra without altering binding chemistry. We include GABA-A receptor containing membrane fragments to ensure the rig can detect known anesthetic effects in a separate substrate. If the microtubule signal vanishes while the membrane signal behaves as expected, that's also data. Everything is time-stamped, and an independent auditor watches the blinding and post-log. Analysis isn't a magic show. We publish the code beforehand, how peaks are detected, how Q is estimated, how outliers are handled. We specify the models we'll compare: a classical damping model based on viscosity and dielectric shifts, a pocket occupancy model, and a collapse timescale aligned model where one latent timescale governs the crossing point of dose-response families. Bayesian model comparison decides which story fits with the fewest adjustable knobs. If none fits, we say so. Then comes the pass-fail. Pass means 4 things happen together across labs. 1. Clear. Reproducible resonances appear in polymerized microtubules and vanish or change qualitatively in controls. 2. Anesthetic damping scales with potency after normalizing for pocket occupancy, and a non-anesthetic analog fails at scaling. 3. Xenon pressure shifts both potency and damping in lockstep. 4. Cavity versus open differences persist after classical. Band tied to an objective reduction timescale estimate. Miss any pillar in the lambda orchestra, our coupling claim steps back or retires. To keep us honest, we stream select runs live. Cameras show the rig, the temperature readouts, the pressure gauges, and a real-time spectral waterfall. The sample identities stay blinded on screen. Viewers see every hiccup. Ground faults, clogged channels, drift, and auditors can call timeouts. When the code unlocks the blinding, everyone sees it together. If the curves refuse to collapse, the world watches us say so. What happens if we pass? The bridge doesn't become a highway. It becomes a beam you can step on. We'd still need in vivo extensions, HMEG timing signatures that move with the same levers, psychophysics that shifts by predictive millisecond increments, and anesthetic microdoses that bridge protein physics to behavior without confounds. What happens if we fail? We publish the failure, retire the lambda coupling, and keep whatever we learned about microtubule biophysics and anesthetic action. Either way, the field gets cleaner. This is the point. Stop arguing in conference hallways and let numbers push back. Make it brutal, make it public, and let the vacuum either whisper through proteins or not. Whatever the outcome, the philosophical bill comes due next. If mind and cosmos touch, and if they don't, picture 2 paths laid out on the bench after the data drop. On path A, the curves line up. The damping versus potency plots from the microtubule assays cross where the pre-registration said they would. Xenon's pressure shifts match both clinic and chip. The cavity versus open contrast survives nuisance controls. Then EEG and psychophysics echo the same latent timing under safe perturbations. Suddenly, a conscious moment looks like an objective physical event, one that happens when a mass distribution threshold is met on a clock that whispers the same constants that sculpt the sky. If that holds, mind becomes a cosmobiological process. Not magic, not outside physics. Something like this. Neurons set the stage with classical computation. Microtubule lattices supply structured sites where collective modes can form. Objective reductions snap potentials into events on a schedule determined by gravitational bookkeeping that might include a background term. Those snaps don't command galaxies. They share a rule with them. In that reframing, free will stops being a ghost and becomes a question about how systems shape which ensembles reach threshold, how intention, training, and context bias, which collapses, are orchestrated next. Meaning shifts from my brain hallucinates a world to my experience is a lawful series of events in a universe whose laws also run the stars. Path A also gives medicine new questions. If conscious episodes rely on orchestrated reductions, anesthesia is timing control. Could safer sedation tune the same modes more narrowly? Could disorders of consciousness be partly timing disorders, frames failing to stitch, treatable by general entrainment that restores the cadence? Guardrails would be strict. No claims without trials, no hacks peddled on hype. But the map changes. Consciousness research becomes metrology. Count the events, model their coupling, predict their perturbations. There's philosophy to clean up too. Panpsychism loses both the romance and the burden of saying everything feels. In Path A, feeling isn't ubiquitous. It's wherever objective reductions are orchestrated by living architecture into integrated moments. The bridge doesn't blur categories, it tightens them. And Why Now gets a sharper selection story. Observer epochs are those where biology's ladders can climb to the collapse thresholds that make awareness rich. Now take Path B. The curves don't cross. The blinding unlocks the mush. No cavity effect after classical corrections. Xenon's pressure shifts behave in membranes, not in tubulin. Psychophysics bends with stimulation and oxygen as networks predict, not as a collapsed timescale model would. The lambda angle evaporates. Orchestro. R, at least in the microtubule form and with a vacuum dial, retires from the main stage. What remains is not a consolation prize. It's a clean field. Anesthesia research sharpens around known targets, GABA A and MDA, 2-POR-K plus channels, and the way network inhibition breaks ignition and thalamocortical routing. Microtubules return to their proven roles: scaffolding, transport, plasticity, and perhaps classical electromechanical resonances that influence synapses without needing coherence. Quantum biology keeps its wins: photosynthesis, magnetoreception, tunneling, while neuroscience stays honest about scales. The hard problem doesn't fold, but the search space shrinks. Global workspace, IIT, predictive processing, and newer hybrids fight it out with better constraints. We keep asking why spikes aren't blue, but we stop pretending gravity will answer. Path B also gives us ethics with fewer traps. No one sells vacuum hacks for the brain. No pop mysticism about manifesting reality sneaks in. We still measure, prod, and model, just with different priors. Perturbational complexity remains a solid clinical marker. Timing windows still matter as network properties tied to metabolism and inhibition. The romance goes down a notch, the rigor goes up. Either way, careers pivot. On Path A, a postdoc known for careful nulls becomes a person who showed a tiny vacuum fingerprint in a protein, then spends a decade beating their own result with stricter rigs. On Path B, a theorist who loved the bridge writes the best refutation and earns trust for telling the truth. Students learn the difference between an exciting idea and an accountable claim. Labs that pre-registered and streamed their failures get cited for how to do hard experiments in public. The human stake across both paths is the same. We're asking what gives value to a moment that can go missing under a mask. If the cosmos touches that moment, it's humbling. If it doesn't, the moment is no less rare. In either case, curiosity survives by discipline, precise questions, clean controls, and a willingness to walk away from our own stories when the numbers say so. And there's a middle possibility worth naming. The microtubule vacuum story might be wrong. While a different quantum classical scene still matters: spin chemistry and receptors, unconventional ionic conduction, mesoscale criticality that fakes some quantum signatures. If so, Path B isn't an ending, but a fork towards subtler physics that doesn't need lambda. Or Path A might be half right. Objective reductions exist, but biology doesn't use microtubules to orchestrate them. Then the bridge shifts substrate, not destination. So we set guardrails now. No medical claims ahead of evidence. No conflation of dark energy with fuel or force. No metaphysical add-ons smuggled in as implications. Open data, open code, independent replication. Invite skeptics to wire the grounds. If the link lives, it'll survive the light. If it dies, the light will have done the work. Either path leaves us with a simple practice: respect experience by measuring it well. Ask tight questions. Let them hurt a little. Then follow what holds up. Myths, grifts, guardrails. Let's clear the fog before it turns into smoke. First myth: thoughts control reality. They don't. Your intentions can shape behavior, and behavior reshapes environments, but there's no evidence the silent wish tweaks cosmic parameters, even in the boldest version of our bridge. Conscious moments are physical events timed by laws. They aren't magic wands. If anything, the claim ties mind more tightly to constraints, not less. Psychological note: the clearer we set expectations, the more the audience trusts the next claim and shares it. Second myth: dark energy is fuel you can tap. It isn't a tank. In the equations, it's a parameter describing a uniform energy density that drives expansion on cosmic scales. You can't bottle it or burn it. Calling it a force inside your head is metaphor, not mechanics. The honest version says, if vacuum structure enters collapse thresholds, it's through timing biases too tiny to feel, not a push you can surf. Now the Grifts. Every time a serious field brushes a deep question, someone sells shortcuts. Quantum disks, consciousness that stickers for your water, raise your vibration, and manifest abundance cloaked in half-remembered equations. The pattern is consistent: vague illusions, no pre-registration, cherry-picked graphs, proprietary devices, paywalls around protocols. When you see a dramatic before or after without blinding or controls, assume you're the product. Guardrails start with language. We say hypothesis, not proof. We separate consistent with from, caused by. We never promise medical outcomes. No brain hacks, no treatment claims, no wellness spins. If a result touches patient care, it enters a trial with oversight, endpoints, and the risk that it fails. If we mention dark energy, we define it, we don't romanticize it. If we say collapse timescale, we show the math, we list assumptions, we name what could break it. Guardrails continue with process, reproducibility over rhetoric. Pre-registered protocols, blinding independent replication, raw data, and open code. We don't tune analysis after peaking. We don't bury nulls. We stream the boring parts, the drift checks, the ground maps, the calibration failures, because integrity lives where nobody's clapping. We welcome people who think we're wrong to watch us set the baselines. We invite statisticians who don't care about microtubules to design the model comparisons. Media literacy keeps the edges clean. When a headline says, "Scientists prove consciousness is quantum," ask, where's the preprint? Is the journal reputable? Are there replications? What are the effect sizes and error bars? Did anyone blind conditions? Does the conclusion match the data or the press office? Learn to spot hype words, revolutionary, paradigm-shifting, mind-blowing, and translate them to probably early, maybe fragile, needs checking. Learn to love method sections. That's where truth hides. Seductive bridges attract bad actors because they promise meaning without discipline. They also attract honest curiosity. The trick is to protect the latter from the former. One way is to keep metaphysics out of lab notes. No universal consciousness claims smuggled into discussions of tubular binding. No, the universe wants to know itself stitched on the Q factor plots. Those lines might feel good. They don't help an experiment survive. There's a fine line between a metaphor and a trap. Calling consciousness the dark energy inside your brain is a hook. It isn't a literal statement. The literal work is harder and narrower. Does damping of specific microtubule modes vary with anesthetic potency across chemistries? And do those curves intersect where a collapsed timescale model says they should? If yes, we publish the numbers and still avoid mystical overreach. If no, we publish the numbers and drop the metaphor. Another guardrail: never sell access. If we build the experiment, the plans are public, the parts list is public, the data are public. No VIP tiers. No premium consciousness club. If there's a crowdfunding page, it buys optics and pays grad stipends, not yachts. Donors get the right to see failure in real time. They don't get secret results. Finally, protect people. Vulnerable folks searching for meaning or relief are the easiest marks. So we repeat, often this project won't cure disease, repair trauma, or replace therapy. It won't unlock hidden powers. It might, at best, show a small physical signature that tightens theories and helps anesthesiology a little. That's enough. Science earns trust by refusing to promise more. We return to the one stake that matters. Curiosity deserves clean conditions. If there's a bridge, it will stand under weight. If there isn't, integrity means walking away without bitterness. Keep your wonder. Guard it with methods, and bring the question back to the smallest scale where it lives, the moment you call now, which needs no hype to be worth protecting. The personal scale of a cosmic question. A streetlight hums. Tires hiss on wet pavement. On a night walk, you notice awareness noticing itself. No fireworks, just a steady presence riding the city's noise while the sky above is still and forever stretching. You don't feel expansion. You feel the cold on your hands, the tightness in your shoes, the quiet surprise that you're here at all. That's the only aperture you get. Small, private, and somehow pointed at everything. You've heard the arguments, the equations, the careful maybes. None of them replace this one window. Whether microtubules carry resonances or networks alone stitch perception, your now is the instrument that registers it. When anesthesia erases it, a life pauses. When it returns, the world rushes back with the relief of a breath you didn't know you were holding. So bring the question down to what you can actually do. Pay attention to timing, how a melody clicks as one phrase, how two footsteps merge into a single beat when they're close enough, how a flash gets easier to see with a tiny tone before it. That's your lab. And if we build the other lab, the chips, the optics, the preprint logs, you're still the witness who decides whether the curves mean anything about a life lived in moments. Wonder doesn't need mythology. It needs precision. You ask, you measure, you let the answer land. If it lands on a bridge, you follow it carefully. If it lands on a wall, you don't paint a door. You move on. Either way, the practice honors the one resource that doesn't inflate with the universe, a moment of clear attention. Maybe the universe's strangest pressure touches the only thing that can feel it. Get brief, aware now. If you want to see us try to catch that touch on a scope, join the build. Subscribe, hit the bell, and watch the pinned episode where we pre-register, stream the runs, and let you tear the protocol apart in real time. Then share it and start a fight in the group chat.